So, hi everyone, welcome to TMLS. We have Bhaskarjit Sarmah as our speaker for this session. Bhaskarjit is a data scientist and has solved business problems in many domains, including retail, FMCG, banking, media, and entertainment using machine learning. Currently, he's working as a senior data scientist at BlackRock, where he builds predictive models for financial markets. His research interests are network science, AI interpretability, and uncertainty and NLP. In this talk, we will be hearing about learning embedded representation of the stock correlation matrix using graph machine learning. I'll give the stage to you, Bhaskarjit.
Yeah, thank you so much, Anita, for the introduction. And I'd like to welcome everyone to this presentation. So today I'll talk about, or I will take you through one of the paper that we have published this year. The paper titled Learning Embedded Representation of the Stock Correlation Matrix Using Graph Machine Learning. And this paper is co-authored by Nayana Nair, Thagash Mehta, and Stefano Pascali, who are colleagues at BlackRock. So here, today we'll talk about this paper, and the main essence of this paper is to create some sort of embedding representation to denote stocks. When I say embedding representation, I mean a vector of some dimension which is used to represent stocks in S&P 500 universe. So here's the agenda. So first I'll talk about problem statement, what exactly the problem statement we're trying to solve. Then I'll talk about very briefly about word embeddings, because we have used word embeddings as inspiration behind stock embeddings. And word embedding is a very popular in natural language processing. It's a very popular, or in fact, a state-of-the-art feature extraction process for extracting, numerical representation of text data. So then we'll talk about how we created these stock embeddings. We'll talk about the data preparation process. We'll talk about the methodology, and we also talk about evaluation of those embeddings and few use cases. So let me first talk about the problem statement. So in many domains, including financial, sector, there is a relationship between different financial securities exist, and there are many applications across asset management, in, like, for example, risk management or portfolio construction, and even trading strategies, where understanding network and topological structures of financial instruments is very, very helpful to analyze. For example, in risk management, if, for example, one stock goes down, then what will be the impact of that stock across the portfolio, for example. You can also use the interconnectedness of security to create portfolio construction to give how much weight we should assign to one particular stock in a portfolio, and so on. But traditionally, these network analysis have been done by using some kind of hand-generated features like different centrality measures, like degree centrality, closeness centrality, betweenness centrality, eigenvector centrality, and etc. And you have few other metrics like connected components, average path length, and so on. These kind of hand-generated features traditionally have been used to understand the interconnectedness property of these financial instruments. But in this paper, here we're trying to attempt to automate this feature extraction process by training a neural network model on a network of stocks. And in this case, we have taken S&P 500 universe to create an embedding representation for each stock. So here is the bird's eye view of this methodology. You have a network of stocks, and then you pass this network of stocks on a top of a neural network, and then you get this bars. For example, these are a vector which is denoting each and every stock. So here, these nodes, these are the stocks, and these edges, these are some connection between or edge between two different stocks, and this bar, different colored bars, these are the embedding representation. So this is what is our goal that we want to obtain from this entire computation or analysis. So, where these embeddings can be useful? So, these embeddings can be used in many different downstream tasks. For example, we can use these embeddings as a feature in machine learning models instead of using any different techniques like one hot encoding. If we want to include stock ticker, for example, as a feature, we can use their embedding representation instead of using any other different categorical encoding techniques. Then it can also help us to identify structural analysis of a complex network, how a, for example, S&P 500, how it behaves under certain market condition, when markets are in stress condition, or when markets are stable. So how does this behave in a certain way? We can analyze using this learned embeddings. We can also use this embedding to find similar or dissimilar stocks within a sector or in different sectors, which will be helpful to create some kind of stock recommender systems. Also, we can use these learned embeddings to perform analogical inferences on learned embeddings, and this information or knowledge can be helpful for investors who want to do some kind of portfolio diversification, for example. So there are a lot of different applications are there, which will which I'll explain as well towards the end of this session. So let me first take you through the inspiration that we have used here for creating stock embeddings, that is word embeddings. So here, for example, if I ask all of you to fill in the blank in this particular sentence, I am dash the notes. Well, some of you might be thinking, okay, it can be filled in by the word, studying, or reading, or writing, or taking, for example, right? So there can be so many different options you might have: reading, studying, memorizing, reviewing, writing, and so on. So, what's the idea behind word embeddings? So, this idea of word embedding was put forward by the team of researchers at Google. And the idea here is that if two unique words are frequently surrounded by similar sets of words when used in various sentences across a large corpus, then those words tend to be related in their meaning. For example, if the word reading or studying, these two words are frequently surrounded by the similar words like I am, the notes multiple times, then the word reading and studying will be similar in meaning. So this is the idea put forward by team of researchers at Google when they first created word-to-vec algorithm to come up with word embeddings. So here the objective is to predict the center word given its surrounding words for all the sentences in a given corpus. So that is the idea. So how we learn these embeddings. So here the data preparation for word embedding is: first you need to identify a text corpus, that is the collection of documents for which we want to compute word embeddings. Then from the text corpus, create sets of context word and center word using a moving window of fixed size. So why we need a moving window fixed size here? Because the sentences can be of different length in a corpus, right? Some sentences might be of length only word having 7 words. Some sentences might have 10 words. Some sentences might have 5 words only, and so on. So here, for example, this is one sentence: movie was awesome and a must watch. So here you fix a window size of 5. So if you fix the window size of 5, then the sentence will be movie was awesome and a. So here awesome will be the center word. The word movie was and they become context word. And then what you try to do, you try to predict awesome based on the context word movie was a must. Then you move the window, sliding window by 1 unit towards the right. in that case and become the center word, and remaining others become context word, and so on. So you keep on doing the same thing till you reach the last 5 word in the corpus. And once you do this, then you get this data set which looks like this. You get a set of context words. You get one single word in the center word. So here context word, length of context word will always be 4, and this is the only single word that we try to predict. And then you just try to create a shallow neural network. So for example, here you pass in all the center word, and you try to predict the the context word. And then you once you train this model, then you get these two vectors, matrices, weight matrices w1 and w2. And once you get these two weight matrices w1 and w2, you just take an average of these two weight matrices, and that becomes the embeddings, learned embeddings. So the word embeddings in this process is just a byproduct of predicting the center word. So this is the exactly same methodology we'll be using here as well in stock embedding. But the problem in stock embeddings here is we do not have any sentence-like structures that we have for NLP. So how do we create the sentence-like structures? That's what I'll be explaining in the next slide. So so here to create sentence-like structure, we first started with creating the getting the raw data. So the raw data that we used was we computed log returns for S&P 500 universe for an entire year. From that log return, we created a correlation matrix of log returns. So this is what you can see. This is the correlation matrix of S&P 500, where correlation goes from -0.25 to 1. And then we create a network of stocks with each stock as the node, and edge between stocks correspond to their respective correlation. So here each and every circle is a stock, and then each and every edge is a pairwise correlation. So this kind of network, which you can see, is known as a fully connected network. But fully connected networks are actually not very meaningful in the sense that they contain some noise as well. For example, if you see this matrix in the diagonal, so the diagonal is always 1 because I'm computing correlation with itself. So if you convert this matrix into a network, then you will also get a lot of self loops. So those self loops are not important for me. And there will be certain edges where the correlation will be also very small. So we want to get rid of those self loop or those small correlation or any other unnecessary information. So we want to filter this correlation network of stocks which we got from correlation matrix. But we cannot directly filter it as it is. We first convert this correlation matrix into a distance matrix. So here, to remove this noise from network of stocks, we convert correlation matrix into distance matrix using this formula, that is square root of 2 into 1 minus correlation. So here, this is the correlation matrix, and this is the distance matrix. And distance matrix always lies between this range of 0 to 1.4. Then we'll find out, create another network of stocks using this distance metric, and we'll apply the algorithm minimum spanning tree to filter that network. So when you apply minimum spanning tree, it will only goes through, or it will only contain or capture those connections between nodes where the values are minimum. That means distance is minimum. So when distance is minimum, correlation will be maximum, and that's what we exactly wanted. So in the next slide, you'll see, so this particular network is again fully connected network that we got from distance matrix, not the correlation matrix. And now since distance and correlation are inversely proportional to each other, And once we apply minimum spanning tree, it will capture only those edges where distance is minimum. That means correlation will be higher. So once we apply minimum spanning tree on top of distance matrix, then this is what we get as an output. So this is what we had originally, the raw data, the correlation matrix from log returns. And then after converting this correlation matrix to distance matrix and then applying minimum spanning tree algorithm, we get this filtered network of stocks. Now, once we get this filtered network of stocks, now we are ready to create sentence-like structures using another algorithm called random walk algorithm. So again, in this random walk algorithm, we have four different hyperparameters. Hyperparameter R, that means how many number of random walks we want to create from each node in this graph. Then second hyperparameter is the length. What is the length of this random walk? It should be 50, it should be 100, and so on. And each walk is controlled by another two parameters called P and Q. So where the probability of P is once we move from one node, then what is the probability getting back to that node? And probability Q is the probability of getting away from that node. So these are again hyperparameter which we have tuned to evaluate the learned embeddings in a quantitative way, which I'll explain in just one of the upcoming slides. So how do we create sentence-like structure from this minimum spanning tree? So let's imagine you are standing at this node, Facebook. Then you have many different directions to go to. You can go to Citibank, then Nokia, Nvidia, Twitter, and so on. So let's say I'm randomly moving to City. Then from City again, I have three different options. Let's say I'm moving to ET. Then ET, I have two different options. But since because of the parameter P, that means probability of getting back to the node from where we started the journey, it will move in the opposite direction. So from ET again, we move to City. Then from City again, we move to Facebook. From Facebook, we move to Microsoft. Then Microsoft to again Facebook. Sorry, Microsoft to Alibaba. Then from Alibaba again to Microsoft. Then to Apple. Then to AT&T. So now what you see on the right hand side, this is a sentence like structure just by doing one random walk. So we repeat this process multiple times. And when we repeat this process multiple times, we get this kind of an data set, sentence one, sentence two, and so on. And then again, we use the same approach that I have explained in Word to Vec for word embeddings. That again, you create a particular window, sliding window. So again, let's say I'm using the sliding window of size 5. So in this size 5 window, so I want to predict the center stock, that is TGT, based on the context stock, that is ALGN, NOW, and ATR. So this is the first data point that I get. Then you move the window by one more unit. In this case, NOW becomes the target stock and remaining everything else is the context stock. So you keep on moving this sliding window till you reach the last 5 stocks of this data set. And then you create this, then you completely fill up this context, the data set of context stock and target stock. Then you again create this shallow neural network, train this shallow neural network using this data set. So here, this number of neuron in this hidden layer actually decides what should be the dimension of your embedding. If you keep this number of neuron as 16, for example, then the number of dimension of the embedding will be 16. If you keep it 32, then it will be the number of dimension of the embeddings will be 32. So this also acts as a hyperparameter when we train. So once these embeddings are learned, we can use it in many different downstream applications. And before that, we also did some quantitative evaluation of embeddings as well. So these are the uh, six different hyperparameters. This L, R, P, Q. These are the four hyperparameters of random walk algorithm, which we discussed already. Um, then W is the window size, and this DIM is the dimensionality of the stock vectors. And we created multiple clusters of stocks using this learned embeddings, and then evaluated against the GICS categories using V-measure. And we have compared against industry sector, industry group, industry subgroup, and then we took the average. And this particular combination gives the best possible result across all the different groups. So this is only one way of evaluating these embeddings, but we can also do qualitative evaluation of embeddings as well, which I'll explain in just a few minutes. So the first use case is that this learned embeddings can be used as a feature for downstream analytics. So what do I mean by this is, so for example, let's say here you are trying to solve a classification or regression problem, and where the stock tickers act as a variable here. You want to include this as a variable, S&P 500 stock tickers. Now, what is the traditional way of handling this kind of nominal categorical variable is that you create a one hot encoding representation. Now, when you create one hot encoding representations like this, then there are two different problems exist. One is it increases the feature space. So right now we have only 10 independent variables, but if you create a one hot encoding representation of S&P 500 universe, then we will get around 508 number of features instead of 10. So this will increase the feature space significantly, thereby reducing the predictive power of the dataset. And the second disadvantage, if you see here, the stock Apple and Microsoft, they seems like they're completely independent of each other, but actually they are not. They're coming from the same industry. They will have the same similar kind of correlation as well, but it is right now taking this into account that they're completely independent of each other. So now using this embeddings, the embeddings that we have learned, what we can do is, instead of not using one hot encoding or dummy variables, we can simply create an aggregation of those embedding. Let's say you just take average of the embedding that we have learned, and replace those stock tickers by the average of the learned embeddings. And the advantage will be the feature space will not increase. And also, if you see the first value 1.68, that's for Apple, and the third one is for Microsoft, which is 1.64. So they're almost on the similar lines, which also tells you that they are kind of related to each other, not completely independent of each other. Then the next, and similarly, what we just have created for embeddings for stocks, the similar embeddings can be learned for different sectors or different broker dealers, for example, in fixed income markets as well. Then the second use case is these learned embeddings can be also useful for doing analogical inferences, and it can be useful in an investment context. For example, when investors wish to extend their portfolios in different sectors, but they do not have much experience in those sectors, or to improve portfolio diversity. This is again inspired from NLP. In NLP, you have this kind of analogical inferences that if man is to women, then king is to what? King is to queen. So similarly, if JPM if JPM is to Goldman, then Microsoft is to. So Microsoft is to, this is the list of recommendations. That is Microsoft is to Google with a similarity score of 0.882. Okay. Then if JPM is to Goldman, then Johnson Johnson is to Amgen with a similarity score of 837. Then second is BMI, LLY, and so on. So these are all pharma companies, which is again Johnson Johnson belongs to. Then it can be also useful for identifying nearest neighbors. So for example, here, if you want to find out which are the stocks that are most similar to JPM, so JPM is the query stock here, and then it will give you a list of all those stocks with their similarity score. And if you see, these all the stocks there come from financial sector as a JPM. And you can also do, for example, do this kind of analysis. For example, which stock is most similar to Google out of these four: J&J, MS, MOS, and FP. So Johnson and Johnson is pharma company, Morgan Stanley finance company, MOS, this is a chemical fertilizer company. So out of all these four, Facebook and Google is most similar. Then doesn't match out of JPM, Morgan Stanley, Goldman, and Google. So JPM, Morgan Stanley, Goldman, they're all financial sector, but Google is technology. So Google does not match. So this kind of analogical inferences can be done, and this is also useful maybe to create some kind of recommender system for stocks. So these are some of the use cases and the future research and in directions what we are trying to do. So here we are using simply the log returns, and then we're computing the correlation matrix. But apart from using this log returns data, we also have some other ideas of using different alternative data sets like NLP data set. Like you can use sentiment from news or SEC filings to create or to come up with a correlation matrix and then do this analysis. Then another approach that we are thinking of, then instead of using minimum spanning tree, which actually reduces some information, we can use some other techniques like PFMG, planar maximally filtered graph, or random matrix theory, which capture most of the information. And also using different algorithm instead of using random walk. For example, there are other algorithms like deep walk, which we are yet to explore. And also the quantitative evaluation that we have done here is using a clustering based approach and using v measure. But we're also thinking of using different kind of problems, like use this embedding as a feature to come up with some link prediction or node prediction in a problem, and then see how many those links or edges these learned embeddings are able to identify or predict. So these are the future research in this direction. So yeah, that's it from my side. I'm open for any questions if you have.
Thank you for the great presentation. There are a bunch of questions on the right side if you want to choose which ones to answer.
Okay, let me stop sharing my screen then. Okay, I can see the questions now. Okay, so the first question, are the initial embeddings one hot encodings? Initial embeddings, what do you mean by initial encodings? The input encodings to the model itself, the shallow neural network. If that's the question, yes, that's right. Okay, the second, yeah, but it's Node 2 vec. So Node 2 vec, here we are using Node 2 vec to create the sentence like structures. And that's it. But to create the embedding, we are using this word 2 vec algorithm, where we are training the shallow neural network. So Node 2 vec is just to create the sentence like structures, because using the correlation matrix, you cannot just create a sentence like structure. Okay, so the second question by Charles is the initial embeddings are randomly initialized weights. Yeah, that's right. So the how this word-to-vec algorithm work is, so as I mentioned, the embeddings that we get is the average of W1 matrix and W2 matrix of the shallow neural network. So when you start the training process, those matrices are randomly initialized. And once you minimize the cross entropy loss, categorical cross entropy loss, then you get the optimal value of those embeddings. So Subhash is saying question end goal of this project approach. Sorry, I joined late. Okay, so the end goal is to create a vector representation of stock. Yeah, that's right. Is you say it looks like stock to vector. Yeah, that's right. Okay, so Subhas, your question is, I see you use log returns as a feature and created correlation, distance matrix, build MST, generate random walk, build training samples, shallow neural network. Have you tried other features while creating correlation? Yeah. what features could be. Yeah, so that's exactly what I mentioned, Subhas, at the last of this presentation. So currently we're also thinking of using alternative data sets like text data. Maybe we can come up with some kind of network using SEC filings, for example. Or but again, SSC filing we get only once a year, only one document. Apart from SSC document, maybe we can also use some sentiment or news sentiment data. So that's what we're also thinking as a next step, future step in this direction. So do you think, Charles, do you think there is a value in trying graph neural network on MST instead of random walk and what to vec? Yeah, graph neural network can also be very much helpful, but the nature of the data set that we have is we have a matrix, correlation matrix. We do not have any other features. But if you want to include any other features as well, like for all the stocks, what are some P&E ratio and all the other accounting information, maybe we can create some kind of data set where we can use graph neural network. But right now in this approach, I think random walk and what to vec fits better. But yeah, I got your point. To apply graph neural network, we need to have some other features as well, so that we can get everything in a tabular format and come up with some features and create a network out of that, and then you use graph neural network on top of that. So Enrique is asking, has this been taken from theory to practice? Yes, this has been taken from theory to practice. So I'll not divulge too much information, but this is being used or in UAT to find out some new product launches for some ETF, for example, where to find out similar or dissimilar sectors. Okay. So I got another question. Other than the stock itself, are there any other features of stocks? No. So there is no other feature of stock in this graph, but that's what I just described. So we want to use any other information of stocks. Then we can also use a graph neural network, as one gentleman rightly pointed out before. Okay. So was there a reason to show stocks with different colors in the first slide? Are those green somehow? Oh no. So the color in those stock was to show you know uh, which sector they belong to. That's why I have used a different color. That's the only reason. I got one more question, but it's not very clear to me. Question is, why year gain, not day gains? Okay. So you're saying why I'm using yearly data, not everyday data? Okay. Yeah. So right now, this is another consideration that we're thinking actually, and when we pitch this solution to different teams, they also ask the same question that instead of end of day, why can't we do intraday? So at the time, we wanted to make our model much faster. So if you use an intraday data, then it might take some time for comparison. But yes, we can use intraday returns as well, rather than using end of day returns. Yeah, that's a good question again. So yeah, is this applied to portfolio management, and how successful was it, at least in paper trading? Yeah, so this is applied for portfolio management as well. I'll not be able to divulge the exact number here of back testing, but yeah, this has been in production for some of the portfolio management use cases. Okay, I think I have covered all the questions. Over to you, Anita.
Thank you so much. It was a great and amazing talk. I think
Thank
they're
you so much for inviting me.
at 11:30
Thank you.
or 12, but nothing in between. Thank you so much, everyone. Bye.